Push that rock here with Simpson math. Let's discuss rational functions and domain restrictions. This function here has two factors in the denominator, so it's going to have two domain restrictions. Clearly, x cannot be -4 because -4 plus 4 would be 0. 0 times anything is 0. The denominator is 0. We cannot divide by 0. Clearly, x cannot be 3. So when you think about a number line, there's a 3 and there's a -4. X can be any number to the left of -4. It can be any number to the right of 3. It can be any number in between. It just can't be those two numbers. So we say from -infinity to -4. Then we say from -4 to 3. And then we say this union symbol is just how you group or add sets. And then we say 3 to infinity. These parentheses next to the numbers mean they're not included. So -4 is not included, 3 is not included, but every number in between -4 and 3 is included. So this interval notation here describes that interval, this interval describes that one, and this interval describes that one. Over here we see that x cannot be 5, and x cannot be 3, and so it's going to have very similar set interval notation. I'll just shorten the notation and say it can be any real number except 5 and 3. And so there's the domain of two functions. So notice I had it factored. You want to get it factored in order to be able to tell what the domain is. So you factor your denominator, and notice I did not look at my numerator. That doesn't affect the domain. We can divide into 0. We just can't divide by 0. So the whole deal is factor the denominator and look and find the roots of the denominator. Those are the domain restrictions. Okay, now that we know how to find the domain restrictions, let's learn how to determine the behavior at the domain restrictions. The graph may behave in different ways at a domain restriction. So if I want to know, I'm going to concentrate on the -4 restriction. Okay, so I'm not going to worry about this one. We're just going to concentrate on that one and learn how to investigate the behavior. So, and then you can do this one on your own. So let's think about the restriction at -4. That means on this vertical line, I can't see a point because -4 is not in the domain, so it has no output. So there should be no graph point associated with this -4. So, but to find the behavior, what I'm going to do is put in inputs that are allowed that are near -4. So like if I put in a -5, clearly I'm going to have -5 plus 1 is a -4, and then -5 minus 5 is a -10, and then down below I have a -5 plus 4, that's a -1, and -5 minus 3 is a -8. So this is 40 divided by 8, which that's 5. So at -5, I go up 5. 1, 2, 3, 4, 5. Let's find out at -4.5. So I get closer. I went from -5 and I went over to -4.5. And I'm going to see what happens when I put this input in. So -4.5 plus 1, that's a -3.5. A -4.5 minus 5 is a -9.5. -4.5 plus 4 is a -0.5. I'll write it like this, although it is 0.5. And -4.5 minus 3 is a -7.5. Now, when I cut a negative times a negative is positive, negative times a negative is positive, so everything's positive, so we're going to get a positive result. When I cut 7.5 in half, I get, 3 3/4. Because I'm just multiplying by half is just cutting it in half. Now I have 3.5 times 9.5 is 3 times 9 is 27, 4 times 10 is 40, somewhere between 27 and 40, roughly 33. Maybe I should use this symbol because now I'm just roughly approximating. And 4 goes into 32 8 times. So this is smaller than 4, so maybe bigger than 8. But, maybe 9. I don't know. It's close to 9 anyway. So when I got here, I went up 9. So there's 5, 6, 7, 8, 9. So it looks to me like the graph is bending upward. If you want to make sure, put in 4.1. You really should test from the other side as well. Like if I put in -3, what do I get? Well, negative 3 plus 1 is a negative 2. Negative 3 minus 5 is a negative 8. Negative 3 plus 4 is 1. Negative 3 minus 3 is a negative 6. And so a negative times a negative is a positive 16, but down below I have a positive times a negative, so it's a negative 6. If this was 18, it'd be negative 3, so it's not quite negative 3. So I go down not quite negative 3, 1, 2, not quite 3. So probably what's happening is it's stretching down, but you put in negative 3.1 and confirm that you get a lower negative number. So I think what's happening here is we have a vertical asymptote. And this is how you investigate to find out if you truly do. You plot points near the domain restriction. So negative 4.5, negative 3.5, and then negative 4.1 and negative 3.9, and you see what the behavior is. I'll leave you to finish the graph. Let's look at another example. This function may very well have a vertical asymptote at 3. You can investigate. But what's happening at 5? Remember, the domain is, on this one, is any real number but not 5 and not 3. Any other number is fine. We can't allow 5 because 5 minus 5 would be 0. But notice that I can reduce. And so I have a function that's simpler, and it equals that function everywhere except at 5. This function, like that function, is undefined at 3. But this function is defined at 3. If I put in 5, I get 5 plus 1 is 6. 5 minus 3 is 2, and I get 3. So when I put in 5, I get 1, 2, 3. But wait, that 5's not allowed in this graph. Even though this graph gives me an output, it's not allowed in this graph. So this graph must be approaching this point at 5, 3. So there's not going to be an asymptote, because if there was an asymptote, this graph would have to be going up or going down dramatically. So there's no asymptote on this graph. This graph is just, now there may be an asymptote over at 3. I'm talking about at 5 right now. This restriction at 5 is just going to have this little point of discontinuity. Point of discontinuity. So there's going to be some curve, and I'll let you investigate what it is. But I mean, we could put in 0 and quickly figure this out. If I put in 0, I get a negative 1/3. Oh wait, there's a domain restriction at 3, so I need to go past 3. Let's put in 4. 4 plus 1 is 5. 4 minus 3 is 1. So when it's at 4, it's at 3, 4, 5. So it's some graph. Oh, I bet there's a vertical asymptote at 3 based on that. What do you think? If we put in 3.1, well, I bet we find a value up here. So, but there's some graph that approaches this point and does like so. And we call this point here a point of discontinuity. Hopefully you can see what I'm writing on the video screen. So, not always. Sometimes there's a vertical asymptote, sometimes there is not. Math made simple. It's Simpson Math.